Hello everyone, welcome to my YouTube channel. Today I'll be doing Microsoft Malware Classification Kaggle competition. This competition first came into Kaggle in the year 2015, and since then it has been one of the most famous in this area. The dataset of this competition is almost half a terabyte, 500 GB, and to my knowledge it's one of the largest publicly available dataset on malware classification. So the problem here is a multi-class classification problem, that we are given a set of 9 different malware families and then a huge set of files, and the job here is to classify if one of those files belongs to one of the malware families. So of course I will get into the detail. Before that, a quick word on my YouTube channel that I plan to publish and upload videos quite frequently, 2 to 3 times each week. So if you have not subscribed yet, please do subscribe, and if you like the video at the end, please don't forget to hit the like button. Alright, with that intro, let's get into the challenge. And so here is the main competition page in Kaggle, Microsoft Malware Classification BIG 2015. Remember, there are couple of malware classification challenge in Kaggle, but I am talking about this one, which was hosted in 2015 and with the prize money of $16,000. All right, so let's it's an overview page here. Of course, you should read about this one. And now let's go to the data tab, and here is our data. This 37.8 GB, it's a compressed file, and if you uncompress it, it will become almost 500 GB. And as you can see at the top, they are giving indeed a warning that this dataset is almost half a terabyte uncompressed. So when handling this competition, you really have to be patient. You really need a powerful computer, either locally or in the cloud. So I will tell in a second that how I handle this data for my training. So let's first understand this data and what the main challenge here it is. So you are provided with a set of known malware files representing a mix of 9 different families. Each malware file has an ID, a 20-character hash value, uniquely identifying the file. So this 20-character hash value uniquely identifying a file, they are talking about this one, train label.csv. So each of these files, this is a unique hash character, and these represent each file, and those files are in this folder, train. So this train.7z, this file is 18.8 compressed, and if you uncompress it, it will become around 200 plus GB. And each of the file has a name, and those unique names are here, and the class represent one of the 9 classes. Right now here we can only see one. That's because it's a long list, and if we go down, we will definitely see some other class names here. Okay, I cannot yet see because there are really long number of, so total we have something like 10,800 plus files. So anyway, if you go down, you will see other classes here, and actually you have to download these data, so you will see it there. All right, so that's our train label and train 7z. Now let's understand what these malware classes are. So these are the 9 classes that they're talking about: Ramneet, Lollipop, etc., Wundo, Simda. For each file, the raw data contains a hexadecimal representation of the file's binary content without the PE header. So that's these files are within this train.7z folder. And when you uncompress it, you will see 2 types of files. One is .asm and another one is .bytes file. We will know in detail what they are, but for now just know that the .asm file is pretty much their assembly language code files, and .byte files are like hexadecimal file representing the hexadecimal code of those files. And our job is to classify these files to one of these malware.
for the test dataset. That's the whole challenge. Now, when I say classify, what it means is that I drew a quick image of the xi and yi is here. So in this challenge, the xi is your files. So each of this file is your xi, and the yi is this vector of 9 different elements. So 1 2 3 4 5 6 7 8 9, these are the classes, and that's your yi vector. And ultimately the challenge is to assign these probability estimates to each of these class for this file. So for a particular file, at the end of running, say for example random forest or XGBoost, I will come up with a probability estimate that this file xi belongs to class 1 with a probability estimate of 0.2, and the same file belongs to class 2 with a probability estimate of 0.8, and then the probability estimates for all other classes, for example 0000. So of course this number will vary based on different files, and so that's the whole purpose of this challenge, to assign probability estimate to each of the classes out of this 9 for each of the files. And so this is my notebook that I have uploaded to GitHub, and it's also there in Kaggle, and of course I will give the link in the description section of this video. So this is the notebook. It's really a quite long one, so you have to be patient while running it, and I will tell what are the challenges I faced and how you can run this notebook. So initially so ultimately at the end of this notebook I achieved a log loss of 0.007 with XGBoost. That was my best performing model. I tried with various model. I tried with random forest, logistic regression, and quite a few other, and I did some featurization as well. We will get into those details in a second. So this was the best result I had. That's a test log loss. And remember, what was the evaluation criteria for this challenge? That was let's go to overview and evaluation. So this is a multi-class classification problem, so they are using log loss as the evaluation criteria for this challenge, and that's what I applied as well in my notebook. Okay, so I have mentioned all the details in my notebook as well. I also have mentioned all these data and some of the details on the malware that was given. I definitely recommend you go through this notebook. Okay, now coming to my first challenge, running it in Google Colab. So when I extracted the train.7z file, it became almost 250 GB of file after uncompressing it, and that much file I could not really manage even with Google Colab Pro. First I uploaded all this data into a Google Drive of mine, and then of course that's a paid drive space, because normally Google Drive will give you 15 GB. So I have a pro connection, pro subscription of Google Drive, so I get much more space in there. So I uploaded the whole file and then launched a Colab Pro, but Colab Pro could not handle this much of data being pulled from Google Drive. And even in Kaggle I could not run the notebook because I got out of disk space within the first 5 to 7 minutes when I started unzipping the data with these commands. So my final approach to handle the whole training and these full training dataset was this. So I only extracted the train.7z files, which is around 200 GB after extraction in my local machine, and then split that data to train, test, and CV, and that is cross validation. And I ran the whole training only on these 200 GB of data. That is both my training data and test data and cross validation data were created from this train.7z for this notebook. Of course, for submitting to Kaggle, finally you have to run your whole training on these whole training dataset and then submit to be submit your result, submit your submission.csv file to be tested against against Kaggle's own test data. But for the purpose of this notebook, I ran the entire notebook on this dataset, because that's the maximum I could manage with my local machine. And then the next part was training all the data in my machine for all the featurization part, which is mostly CPU based. That is during all the featurization calculation from the files and moving the files and taking the hexadecimal codes out of the files. All these are purely CPU intensive work. That is, they don't make much use of GPU. So all these I ran in local machine. So for these, my entire thing, I only took 50 samples. That is, out of 10,800 train files, I only took 50 .asm files and 50 .byte files, and did all my calculations on those 50 files. And only after I saw that all my calculations are working properly with the parameters and etc. Of course, it will not give you any reasonable prediction result, because you are taking only 50 samples, which are absolutely nothing. But at least you can make sure that your calculation and mathematical operations is running properly on those 50 files. And that's what I did. And those 50 files, even some of the operations, some of the featurization I did on the 50 files, they took sometimes something like 15 minutes or 20 minutes to run. But anyway, so that was my strategy. I did all the calculations on all the featurizations only on 50 files, and only when I saw that the full code is running, the full notebook is running with 50 files, then I finally ran the whole notebook with the 10,800 total number of byte files and ASM files. And then this was the first strategy. And the next second strategy to complete the training session is was something like this, that I created featurization. So this is the featurization I used for this training. We will get into the details of each of these gradually when we go down the notebook. So all these featurization I calculated on the training files, and then combining them, that is the top 2000 bytegram features, top 500 bytegram of opcodes of ASM files, etc., etc. After getting all the individual featurization, and then I merged them and got a merged data frame. And that data frame I exported as a .csv file from my local machine. And then I just upload the .csv file to Google Colab to run the final XGBoost with using the GPU of Colab Pro. So I got a GPU in Colab Pro of Tesla V100, which is pretty powerful with the 16 GB of VRAM capacity. So the final random search CV and XGBoost was run on these combined featurization on the whole data of training in Google Colab. And that final step was quite easy, because quite fast and easy both, because it took the full advantage of Tesla V100 GPU on Google Colab. So yeah, that was my overall strategy. And now we will get into the actual implementation of handling the code and getting the data pre-processed properly, all those details. So just want to quickly run you through the overall approach of this notebook and overall structure and flow of this notebook, so that when you refer my source code either in GitHub or in Kaggle, it becomes much more easier to go through it. So here our input data is just the files. So unlike many other Kaggle competition or many other machine learning problem where we have the input given as in a tabular form or as a data frame, or it given as for unsupervised learning, we are given a set of probably a set of images or a set of text files. But here our input data itself are the files itself. That means we have to structure and get all our features from those files itself. And how many files we are given? We are given 10,868 ASM files and 10,868 byte files. So together almost 21,000 plus files for both of them. So these files itself are our inputs. So we have to get all our features from these files, and that's what is a final featurization that I will build. And these are those features that I build throughout this notebook. And how many features are here? Actually, 1 2 3 4 5 6 7 8, total 8 features that I will build from those files data. And that's what I will go throughout the notebook, the details of which how I build them. But ultimately this is our final featurization, and on this featurization I run the final XGBoost for the final training to get my log loss information. So that was my overall approach for this notebook, and now I quickly will go over the structure of the notebook so that while referring the source code back in Kaggle or GitHub, it becomes much more easier. So in my GitHub, I have given a clear index at the beginning of the notebook, which will make these reading of this notebook easier. So now what I want to mention is about the flow, that I train the classic, a few of the classic machine learning models on first on the byte files only, and then I do the same, that is training some of the classic machine learning model on the Asm files only. And after that, after those individual training separately on Asm file and separately on byte files, then I do the final training on the final featurization after merging all the new features that I build. So this is what you will see in the index as well. So after I do the train test split of the byte files only, I start training only the byte files for different models. So first I train a random model, and then a k nearest neighbor, logistic regression, random forest, XGBoost, and finally I do the XGBoost classification with the best hyperparams. These all only on the byte file. So I have clearly mentioned that these are run only on the byte file. Similarly, I do the same sequence of training, that is k nearest neighbor, logistic, random forest, and XGBoost only on the .asm file. So and then after the XGBoost training is done only on the .asm file, then this is where my final steps begin. So this is the final featurization steps for the final XGBoost model training, and this is where it becomes the final submission training and the most important part. And in this video I am covering these final featurization training steps, because I'm not separately talking about this individual training, because these are almost duplicate kind of thing. So only difference for this individual byte file and Asm file training is that your input data and your Y label is just a different data set. Otherwise everything is just the same. So but I'm mentioning it here because while you refer, if you refer the GitHub code, then while you see these extra codes, it should be easy for you to run through this notebook quickly. All right. And so again, as I mentioned earlier, for each of our xi here in this data set, we are given two sets of file, that is one .asm file and one .bytes file. And based on the analysis of both, we have to come up whether that file is one of the 9 classes of malware or not. So what are Asm files? So we have 10,868 .asm files, and these are mainly assembly language code file, and each of the Asm file contains address, segment, opcodes, registers, and function calls. And we will deal with these opcodes in a while, but before that, just remember these are the contents of an Asm files, and specifically these opcodes part is very important because they have codes like .move, .pos, etc. So if you want to take a deeper look of what are all the possible opcodes of an Asm file, you can take a look at this link. I will post the link to these in the description. So this link was also discussed in the discussion section of this Kaggle competition among the various top leaderboard members. So anyway, so these are the opcodes. Like you can see the push, pop, DEC, INC. These are all kind of assembly language instruction, and they are contained within our .asm files, and that's a very important part of analyzing if a file is a malware or not. All right, and now what are our byte files? So byte files are just the hexadecimal representation of files. So this is a kind of numbers you will see for each of the byte files. They're just hexadecimal representation of file. So this is also a very important part of analyzing and finding out patterns for malware files. Okay, so let's move on to our next section. Now I will start with some very basic EDA, exploratory data analysis, on the distribution of data and our distribution of classes, etc. And now the EDA, and as the first part, I'm importing all the important libraries that is required for this notebook. And just a quick note that for this notebook I am implementing mostly the three classic machine learning algorithms, which are random forest, logistic regressions, and XGBoost. So accordingly, I am importing all the relevant libraries, mostly sklearn, and also another point to note is this package multiprocessing import process. With this process, we can make use of multi-threading during one long, very CPU intensive process that we will come in a minute. So yeah, but other libraries are all the standard sklearn libraries, and along with that, we are also importing Dask. I think I am going to use Dask a little bit because it's a huge data set, and Dask will some CPU based operation can be performed relatively faster with Dask compared to Pandas. Okay, so that's it. And GC, these garbage collection package also will be important here, because these being such a huge data set, and we are calculating so many huge variables during the process, so we cannot keep all those variables in the memory of this notebook as we go down deep in the notebook. So as and when one large variable, after calculation and after making use of that, if I do not need that variable anymore down in the notebook, then I'm going to delete that with the use of this garbage collection package. In that way, I will keep this notebook from crashing. Otherwise, I really faced huge problem in managing this notebook, because if I keep all the variables alive throughout the notebook, then during my later stage work, the notebook crashed. My Jupyter process could not support so much of CPU intensive work. All right, now another point to note that this Microsoft malware is a very famous competition. So the lot of work has been done by data scientists, both professional and data science aspirants. So a lot of code is available indeed in public domain, and I have also referred many of them. I have taken inspiration from many of them, and I will give the source of the codes that I have used here. Some of my code of this notebook is indeed has been taken from some great codes available in GitHub or in Kaggle. So I will keep the reference and the source of those codes here as and when they are used. Okay, so the first point here in this cell I am doing is that separating my byte files and ASM files, because I will be processing them separately. Because they I'm going to do lot of featurization from byte files first and then from ASM files, and so they need to be separated. They cannot be in the same folder, because then I cannot manage them. It's anyway a huge data set of 200 GB. So this cell is pretty much separating them. First I am just with the os.path.isdir, if my destination 1 folder is there, I'm checking that if it's there, otherwise I'm creating it with mkdirs. And then with this part of the code, this code block, I'm just separating the files of ASM to byte files to destination 1 folder and ASM files to destination 2 folder with this shutil.move. It's pretty simple code. You can just take a look at this and you'll get it. And then the first EDA is the classic distribution of classes. So as we mentioned before that this is a multi-class classification problem. So the first EDA is first EDA to check is whether this multi-class classification problem is a balanced dataset or unbalanced dataset. That is whether the classes is distributed more or less equally, or if some classes are underrepresented in the distribution. So this code is just plotting a histogram. I am just it's a simple code. Only special thing I'm making use of that I am including these percentage labels with ax.annotate. So the way that I'm calculating the percentage is with this part of the code, that is 100, and I'm getting the height and dividing it by the total. And what is my total? The total length of y. Remember, y is my class variable here. So when I plot these ax.y-axis.set ticks, yeah, I'm setting a ticks here with 11 ticks, and here also I am getting I'm adjusting the tick levels to represent the percentage. Okay, so this is the plot I'm getting, and the most important thing to look at here is that number 1, number 2, and number 3 is very well represented. Number 3 being the highest of with 27.1% of number 3 classification in the whole dataset. But on the other hand, the lowest one are some of these, that is number 4, number 5, number 7. 5 is almost close to nil. It's only 0.5% of the overall samples are classified as number 5 malware. So this is very low. So overall looks like that this is not a balanced data set. It's, you can say it's kind of unbalanced distribution of classes, where number 1, 2, 3 is well represented, whereas number 4, number 5, and number 7 classes are very sparsely represented. And next I will be creating a box plot of the byte files against the file sizes of the byte files. So for that I first need to extract the file sizes of each of the byte files, and this is very important because file sizes is one of the important features we will be using in our final modeling. So we ultimately will extract the file sizes for both the byte files and .asm files as well. But for now, let's check out the code for extracting the size from byte files. This is the code. It is a simple implementation of the os.stat Python method. So what it's doing is, first I'm creating an array with the listdir os.listdir of my byte files. And remember, my byte files, this folder has been defined here, and this is destination 1, and this contains all my byte files. So, and then I am also making a variable class y. This is the this is from the data frame y class, and then I'm converting it to do list. And remember, what is our y? Our y is the full train label. So we have defined y here. Yes, this code. So y is just the train level.csv after doing it pandas.read csv. And remember, what is our train csv? This is the data given in the Kaggle competition. This is our train level.csv, which contains sorry, all the unique hash codes and all the class labels. Okay, so yeah, so these code for extracting the file sizes make use of this os.stat, and where quickly check out the documentation of os.stat because I will be using it quite a few times in this notebook. Python method stat performs a stat system call on the given path. It returns all these values. st_mode is a protection bit. st_inode is the inode number. I don't need that. What I need is st_size, the size of the file in bytes. Okay, so coming back to our code. So this is just looping through all the files in the byte files directory, and then getting the stat info.st_size, this value, and appending it to an array. And I am dividing this stat size by this number because I need this will give me the file sizes in megabytes. So that's why I'm dividing it by 1024 into 1024. Yeah, and so finally I'm making this data frame which has the ID as a unique hash ID of the file, and then I'm adding this new size column, which is very important, and my class level was already there for each of the file. So okay, with this I can make the box plot now. It's just a simple implementation of sns.boxplot. Here in the X, I'm giving all the classes. I have 9 classes, and Y all the sizes. So this is my blocks plot. But the important point to note here is there's nothing too much decisive to take from this plot. For example, many of these classes are kind of overlapping, like 1, 4, number 6, number 9. They are kind of overlapping. They take the same space in terms of the file size. All right, so that was my box plot, and now the famous plot t-SNE, or t-distributed stochastic neighbor embedding. I'll be using it only on the byte files in this plot, and I'll be using two perplexity, one with 30 and another with 40. Quickly check what the documentation says about the perplexity in t-SNE. So t-SNE is a tool to visualize high dimensional data, which is what our current challenge is. It's an extremely high dimensional. You will see that when you will be done with all the featurization of Asm files and byte files, my total dimension extends to almost more than 1600. So all right, coming back to t-SNE, it converts similarities between data points to joint probabilities and tries to minimize the callback labeler divergence between the joint probabilities of the low dimensional embedding and the high dimensional data. Okay, that's quite a bit of mathematical explanation, but leave that apart. It mainly for multidimensional plotting and multidimensional analysis, t-SNE is very important. It will color code the dimensions and plot beautifully and show that if there is distances, decisive distances between the features in the data set, and the perplexity is the most important parameter that t-SNE takes. And what this means is that perplexity is related to the number of nearest neighbors that is used in other manifold learning algorithms. So this is just the number of nearest neighbor that I want to define, and based on that it will do the whole analysis. So if I take a large number, it will take a larger region of nearest neighbors to analyze the data. So what it says is larger dataset usually require a larger perplexity. Consider selecting a value between 5 and 50. Different values can result in significantly different results, and that's very important. So while plotting t-SNE, you have to kind of experiment with different perplexity values and check whether the resultant plot brings up any conclusive dimension of the data. So sometime when you plot a t-SNE with just number of the perplexity being 5, you will not see any conclusion from the plot. But if you increase the number of this number, you will suddenly see some conclusion coming up from the plot. So anyway, let's check if our case gives any conclusion. So the first plot here, I am just using the sklearn t-SNE and giving the argument as perplexity equal to 50, and ultimately I'm using these matplotlib.scatter to plot it. So this is the plot I'm getting. This is not too much of conclusive. Only one thing we can figure out from this plot, that this color, that is this blue color which represent the class 3 here, that is kind of separable from the other colors, but the others are almost like overlapping. So this was with perplexity of 50. Let's do another plot with perplexity of 30, and this is a plot, but here as well I can see only the number 3 class is separable, but others are kind of overlapping. So for our case in this competition, or for this data set, there is no conclusion that much really from t-SNE plotting. All right, now we did some bit of analysis on the bytes file and did some basic idea on the bytes file. Let's now look at .asm files. And like I said before, that in these train folder we have 10,868 bytes file and 10,868 .asm files. And the .asm files is almost 150 GB out of the 200 GB of train files. And what they contain, these files are again, these files are just assembly language code. I recommend you read a little bit about what exactly is .asm files, because there's a bit of theories out there on this file. Basically, this file contains the address, segments, opcodes, registers, and function calls. Out of these, we will be using the address and opcodes part. Especially the opcodes we'll be using quite a bit to build our features. So what exactly are opcodes? So opcode is a short for operational code. These are the bytes stored in memory that the computer actually runs under the assembly language. So I already mentioned these link here. This is exhaustive list of all the opcodes under the x86 assembler instruction. So like DEC, ADC, POP, MOV, etc. All these are opcodes, and that's exactly what we have in our opcodes files. So we will see that all opcodes that a processor supports in that list, but an assembler basically takes text and does relatively simple conversion of it into a file of opcodes that the computer can read and run directly. Most assemble translate very directly to opcodes, and often the 3 to 5 character assembler names for the opcodes are called opcodes actually. So very technically, the opcodes are the binary numbers stored in memory. The names for them in assembler are the opcode names. Also, not all the binary number stores are opcodes. Opcodes tell the CPU what to do. Just read a little bit. I will specially mention this particular research paper. I have already put the link of these in my notebook here, and I also mentioned it in the video description. That let's zoom in. So here, this research paper mainly says why why the opcode analysis is so important while malware detection. So let's quickly read through it. At least the synopsis. What it says is, to identify malware, most antivirus scanner use combination of signature matching and heuristic based detection. Signature matching compares only to previously known files, while heuristic based detection looks for known system artifacts and previously known bad code pattern in a file. The obvious problem with this is that only known and partially known samples will be recognized. So in this thesis, we use reverse engineering to extract assembly instruction from a given executable file. So this is the most important part that they proposed in this research paper, that they reverse engineered the assembly instruction hidden in the opcodes or of the executable files. We chose to use only the opcodes, which are the part of the instruction that specifies the operation to be performed. For example, MOV. By performing statistical analysis on the dataset, a significant difference between the opcodes in malware and benign files was found. This is the most important key point of this research paper, that opcode is really an important parameter to analyze, to classify if a file is a benign or good file, or if it's an infected or malware file. So that's what they found, that by performing statistical analysis, they found significant difference between the opcodes in malware and benign file. Due to these, supervised and unsupervised machine learning approaches like artificial neural networks, support vector machines, BaseNet, random forest, KNN, and self-organizing map was used to look at the sequence of this instruction. So the sequence of this instruction, that's what opcode will capture. The unknown files were classified as either malware or benign depending on the presence of and number of occurrences of different sequences. We show that by using only opcode without operands, the rest of the instruction malware can be distinguished from benign files by using a sequence length of up to 4 opcodes. A classification accuracy of 95.58% was achieved. This is a great metric that they used only the opcodes without operands, and with that they could detect and they could classify malware with an accuracy of 95.58%. Our work contributes to the research field by proving that. Okay, this is some more information. Anyway, I do recommend go through this blog and in this notebook as well. That's why we work with opcodes and we build features by extracting the opcodes from these .asm files, and so that's very important part of these models that I use, because the final model will have a very important feature that was built with after extracting the opcodes. Okay, now I will build a bag of word feature from the ASM files, and before that let's quickly understand one concept that I will be using quite a bit here, which is Unigram bigram of text analysis, or NLP. So basically Unigram and bigram are very common technique used in text analysis, and to understand conceptually I will refer to this Quora answer. It mentions it very clearly and very simply that what exactly a bigram and trigram etc are, or the unigram. So what they say is that we keep in mind that sometimes word groups provide more benefits than only one word when explaining the meaning. So while doing natural language processing or text analysis, we use word groups rather than the whole sentence or rather than the individual word, because they bring out extra meaning that is valuable for our machine learning model. So for example, here is our sentence: I read a book about the history of America, and the machine wants to get the meaning of the sentence by separating it into small pieces. How should we do it that? How should it do that? It can regard words by one, which is unigram. So each word is a gram. So I read a book. Each of these separate words, they are just unigram because they take a single word from this sentence. Now bigram. So bigram would be I read a book. So they are taking each sequence of two words combination. I read is one sequence, that's one bigram. Then read a is another sequence, which is the next bigram. Then a book is the next bigram, and so on. And similarly the trigram would be I read a book about, etc. So in this model here, in this notebook for analyzing the byte files and the ASM files, I will also be building unigram and bigram features from the files given from the file information, and we will get into that part in a second. And also quickly to get the number of n-grams in a sentence, we can use this formula here. This is part of my notebook. Currently I'm looking at it in VS Code. I will update this in GitHub, so you can check it out in the notebook as well. That if x equal to number of words in a given sentence, the number of n-grams for a sentence would be n-gram equal to x minus n minus 1 in bracket. So for example, if my x equal to 6, that is number of words in a sentence is 6, and I want to calculate the unigram, so the number of n-grams would be x minus n minus 1, which is 6 minus 1 minus 1 equal to 6. That is, unigram is equal to the number of words in a sentence, which is obvious conceptually. And now for bigram, for the same sentence which has 6 words, and I want to calculate the bigram, which is 2. That means the number of bigram possible is 6 minus 2 minus 1, which is 5. All right, and now a very important portion of the whole project, which is a bag of words feature on the ASM files. So what I want to do at the end is I take all the ASM files and I want to create a data frame like this. So to explain this data frame, So these are individual files denoted by or identified by this unique hash ID, and all these features that you see on the top, header.text, .pav, .idata, these are all keywords or opcodes taken from the ASM files, and they are all features. And all these numbers are the frequency that this feature is occurring, that many numbers. So for example, for the first file, the word header occurred 19 times. Similarly, this particular string .text colon, it occurred 744 times. This code .idata occurred 127 times. So this just gives all these codes and how many times they occurred in each file. So as you can imagine, this is just a plain simple count vectorizer function of scikit-learn. But and what does the count vectorizer do? That it just gives a count frequency of a particular text in a sentence or in a text corpus. So that's what I want to do. But the problem here is that I cannot run count vectorizer on 150 GB of data. Our .asm file total is around 150 GB, and a count vectorizer cannot handle that much of data in it. I have tried running that, and it did not run properly. It failed the execution. So that's what my target is. And why this is important, because this is going to become one of the very important feature for our final model, that each of the opcodes and how many times they occur. And remember, we already discussed that how opcodes and their occurrences and their sequences are super important for classifying if a file is benign or it's a malware. So to do that, we need to create these data frame where I can get all the frequencies of each of these codes occurring. And how do I get this each of these feature name? Let's come to that. So all right, so these features now comes under okay, first of all, this code, this particular code, this is I have taken from this GitHub repository. You can check it out. You should check it out indeed. It's a very beautiful, intelligent piece of code applying multi-threading to develop these data frame that I want to do, that is count vectorizer, custom implementation of count vectorizer for our 150 GB of ASM data files. All right, coming back to our point, that how do I decide the 52 features that I just shown here, that these total number of features, I took 52 of them, and that is that after from this code itself, and this code refers to a lot of blogs and research papers, and they found out that this particular set of 52 keywords denoted within the or captured within the .asm files, they are like the most important in terms of malware classification or in terms of file classification indeed. So you can read about them. A lot of links are given here. So you can read about them in more detail, what these codes are and how they are important, and what are the research papers that were referred. So these 52 codes are divided among four different variables. One is prefix, then opcodes, keywords, and registers. And what this register is and what this opcodes is, that's already, this link will mention it in detail. For example, the prefixes are actually part of this data segment, and this Wikipedia link mentions in detail that in computing a data segment, often denoted as .data, is a portion of object file or corresponding address space of a program that contains initialized static variables, that is global variables, and static local variables. The size of this segment is determined by the size of the values in the program source code and does not change at runtime. The data segment is a read-write, since the values of variables can be altered at runtime. Okay, so you should read about this a little bit more to understand, if you are more interested, what exactly these prefixes are and registers are. But to the whole concept is that these forms the code contains of a .asm file, the assembly line code, assembly line files that we are given, and those assembly line analyzing these keywords are extremely important to take a conclusive decision on the contents of these files, and hence the ultimate purpose of this challenge, that to decide if a file is a malware or not. All right, now before going ahead with this code, a quick concept on the multi-threading, because this whole code implements multi-processing and multi-threading of Python. So let's quickly understand this. So I drew this image just now. So basically, our in the hardware part of our computer, how they are at a very top level, extremely top level, how they are architected is that at the top we have the CPU, and nowadays most of the CPUs are multi-core. So we have, for example, in this architecture we have 4 cores: C1, C2, C3, C4. This is the CPU, and the CPU has a link to the RAM, and this is my RAM, and the RAM in turn is connected to our hard disk, which is HDD or SSD if you're using solid state. So now let's take our example for this malware challenge. So all our data, this huge 200 GB is residing in this HDD, and if we want to read all of them sequentially, it is going to take a long time, and the process will be really time consuming. So we are implementing here the multi-processing technique of Python, and to do that, the fundamental concept goes like this: that the RAM, because it has access to the SSD, it reads data from the SSD, and say for example this data and these 4 data is going to RAM, and then from RAM the processor is processing them. So this particular data point or file can be processed by this first core, then the next file can be processed by the second core, and so on. The third one can be processed by the third core, and the fourth one can be processed by the fourth core. But given it's a multi-core or multi-processed CPU, all these 4 processes can run in parallel, and that's why we are going to use the multi-processing module of Python. This is the module that I'm talking about. I will come to that in the code. So this is multi-processing module, and that pretty much leverages the structure of hardware and processes the files in parallel, or do the computation in parallel. All right, now that we have kind of understood how the multiprocessing architecture works in Python, now we are going to implement the code to do the count vectorizer on the ASM files. And once again, I have taken this code from this repo. So what they are basically doing is they are segmenting the whole 150 GB of ASM files into 5 different folders, and then processing those folders parallelly. So this is the key concept here, and let's look at how this is implementing that. So first I'm creating 5 folders: first, second, third, fourth, fifth. The 6th one is just going to contain the output, and then to move the whole 150 GB of file into this different folder, we are implementing a loop over this range. The range is 0 to 10,868, and why 10,868? Because that many number of ASM files we have under the ASM directory, and then we are just implementing these if else condition with the remainder operator. So if the remainder is 0, then those files goes to the first folder, and if the remainder is 1, then with the shutil.move I'm moving those files to the second folder, and so on for the next 3. That is, if the remainder is 2, then moving to third, then fourth, then fifth, and so on. So now my 150 GB is divided into these 5 folder, each containing around 30 GB of data, and then I'll be processing it parallelly. So now it's a long piece of code. They are just implementing 5 processes, naming them as first process, second process, third process, and basically all this code is doing, all this function, all these 5 function is just the same. And what they're doing is they're just implementing the count vectorizer, that is counting the number of times each of these keywords or each of these 52 selected string that we have selected as to be the most important for the classification of files, and counting how many times they are they have appeared in each file. That's all this code is doing. So I'm not going into the detail in this code because you can just go through line by line and it should be simple enough. And all the second process is just the same as the first process. Then I have fourth process and the fifth process, it is just the same. And then this is the important part. After all the process of all these 5 different functions are defined, then I am here, the multiprocessing concept is implemented. So first I'm making use of this process, because to create a process you have to create a class, you have to create an object of the process class. So you can read more about it here in the documentation of multiprocessing module. So what it says is multiprocessing is a package that supports spawning process using an API similar to threading module. The multiprocessing package offers both local and remote concurrency, effectively sidestepping the global interpreter lock by using sub-processes instead of threads. Okay. Yeah, the process class, this is important. We have to instantiate an object of the process class. So in multiprocessing, processes are spawned by creating a process object and then calling it start method. Yeah, that's important. And that's what this code is doing, that they are creating 5 process object p1, p2, p3, p4, p5 and from the process class. So, and then the start method of process is used to start the thread execution. And then finally using the join method after completion of all the threads. So once a process starts, the current program also keeps on executing. That's a whole concept and the whole purpose here. So in order to stop execution of current program until a process is complete, we have to join them, and that's what it is doing here. So basically here, as a result of using the join, the current program will first wait for the completion of P1 and then P2 and then P3 and P4 and P5 and then join them all together. All right, so now this is done. After this whole thing is done, we will get this data frame. And now the most important point to remember, this whole code execution of the 5 process and doing them in parallel and finally joining them, it took almost like 36 hours to around 45 hours, somewhere in between, in my computer. And in my computer has 8 cores and 32 GB of I have 16 GB of RAM and 8 cores. So you really have to keep your computer completely dedicated to this part for almost 2 days to execute this part of the code on 150 GB of data. And all right, at the end we get this final file. After doing all this process, the whole result of this process is actually exported or converted into a CSV file, and that's being named here as asm output file.csv. And this is the result. This is kind of the result we get, that each of the word 52 featured most important feature words and how many times they appear in each of the files. And we have, remember, we have 10,868 files. Okay, now this data frame is done. This is one of the very important feature we are going to use and finally merge. That will come to after doing something, some more featurization. But now let's move on to our next featurization technique. All right, and before I move to the next section of building the next feature, I just want to put things in the context again, that what we are doing currently is feature engineering on this problem. So basically we are given a huge set of 200 GB files in the trained data set, and we are extracting features from those files here. Because here the problem is very different. Unlike a normal classical machine learning, we do not have a tabular data. We are just given a set of files and we have to build our features from that file. So till now we have just built one single feature, which is this one. this one, what we did in the immediately preceding step, that we extracted Unigram from the ASM file based on the top 52 important keywords. So this is just one feature. We still have to build all the 7 other features that I have listed out, because ultimately all these 8 features will build our final training data frame on which I will run my machine learning model. So let's build the next feature, which is a size of byte files. This is going to be my next feature, size of byte files. I already discussed these, how to calculate size in some time back here while calculating something else. I forgot what was that. But anyway, I will go over this topic again and see what we have done till now. Yeah, so here is that part of the code where I calculated the size of byte files and built this data frame to run my box plot on based on the file size on the y-axis, and on the x-axis was my classes. So yeah, we have already seen this, a pretty simple code using os.stat to get the size of each file, and appending that size as a megabyte into the data frame. And why now this will come into it will make sense when we are building features, that why we needed the size at all, or why we thought of calculating the file size as one of the feature. So let's see this box plot again. So in this box plot, I plotted the file size on the y-axis and on the class, all the classes on the x-axis, and this is only for the byte files. Now, earlier I mentioned that we do not have any conclusion or any conclusive decision from this plot, but just a couple of points to note here, that although some of the plots, some of the box plots here are overlapping, but still they seem to give us some information, like this number 2 class and number 5 class are kind of similar, although a large part of them are overlapping. Why they are similar is because both are within the file size, probably between 4 MB to probably 7 MB. Now we already know the class 5 are very rare. Look at the distribution of our histogram. Class 5 is only 0.4%. So given that information, most of the files during these file size range comes within the class 2. So this could be one of the important information while inputting to our machine learning model. That means that file size may be contributing to the ultimate decision or ultimate prediction of file classification. And so is the case for class 4 and class 6. Mostly they are overlapping, but these two classes again are within a particular file size, and class 1 is also within a very specific range of file size. So although overall the plot does not give any conclusive statement, but it still gives some information that file size can be an important factor in the overall modeling. And that's why we are going to build one of the feature as the file sizes, and we will do that for both the byte file and also the ASM files. And our next feature that I'm going to calculate is the unigram of byte files. And so before we calculate the unigram of byte files, we have to understand one quick concept, that how byte file is constructed, and how their value ranges between 0 to 256. So have a quick look at this. So this is the structure of our byte file. So we already saw this, that the first longer part represent the address, and then we have a pair of letter or number throughout for each byte file. So I have 00008040. Similarly, it could be 80 1C04. So basically, this number and letter combination, this pair ranges between 00 and FF. 00 represent all 0 and FF represent all ones, because each of these represent actually binary format. Means Out of this pair, each of these letter or number represent 4 binary digits. So in this case, FF, the first F represent 4 1, and the second F represent 4 another 4 1. So together 8 of them. So this is the case with each of the representation, each pair, that it's a 8. It will be like this 8 binary representation or 8 binary representation. And because each location can have 2 values, if you multiply all of them, that is 2 into 2 into 2 into 2 in 8 times, you get 2 to the power 8, which is 256. And that's why this number ranges between 0 to 256. And now coming back to calculation of Unigram on byte feature file. Again, first understand that here what we are doing is from the byte files, we are extracting some features. And to do this feature engineering, we are effectively converting these byte files into a text problem, so that we can get some textual analytics parameters. Unigram is actually extensively used in text analysis, in text mining or NLP. So that's what we are doing here. We are extracting Unigram, which is a text analytics parameter or text analytics tool, to be applied to these files, byte files. So here for the Unigram calculation, what we are doing in this part of the code is that the first part, this represents the address. We are completely removing this part first here with the use of I think I'm using okay, that I'm coming in a second. Let's first discuss the concept here. So we are removing this address, and then for the rest part, all this hexadecimal representation, for each pair we are thinking of it as word, and we are getting the word out of that, and we are calculating each of these word how many or each element of this word how many times they occur, or calculating, that means effectively we are calculating the bag of words or the Unigram on each of these words. And to do that, we are removing the space in between and calculating the frequencies that these elements or these part of the words or these each of these pair how many times they occur. So ultimately I will get a data frame like this, that this is a 0th file, this is the file ID, and this is all my features, and that's what these Unigram code calculated above here, that how many times 0 occurs in these, this is that many number, how many times F7 occurs is 2804, and so on and so forth for each of the file. And when I print the shape of the file, which I'm doing 1 second. Yes, so here is the shape of my data frame, which is this data frame has 2 rows and 258 columns. And let's see, this exactly matches what I want. The 258 columns, the first column is just this number, sequence number, and then this one is a ID of each of the file, and this 256 is coming from what we just discussed, that there could be maximum 256 possible values for byte files, because byte files, the way that we discussed, that it ranges between 00 and FF, and between 00 and FF there could be maximum 256 unique values. And that's what we did here by implementing the above code, and that's why I'm getting 258 columns in the final data frame. So basically, again, what I did, what we did here is we thought of each of this pair as a word, and then calculated the bag of words or the Unigram concept on these files. And now this part of the code here, that's where is implementing the count vectorizer or the Unigram or bag of words that I just discussed. And why I had to implement it manually here is because the scikit-learn count vectorizer cannot work with this huge 50 GB of data, because count vectorizer, I think it requires the entire data to be loaded into RAM at once, and loading 50 GB of RAM definitely is not possible in my local machine, and also I do not have a cloud machine where 50 GB of with 50 GB of RAM currently. So and that's the reason these custom built count vectorizer, but this is actually very simple code. It's just building a feature matrix and calculating how many times each of these pair and each of these letter occurs in a single file. That's all it is doing. And why I needed to understand this concept of byte files can have a maximum of 0 to 256 value in between is because look at this, our feature matrix that we are building to calculate this data frame. Finally, it's a 2D matrix, a multidimensional matrix, and one of the dimension of this feature matrix is this maximum value that a byte files can take, 256. So yeah, so this is the final data frame that I get, and this becomes my the next feature, which is unigram of byte files. And finally, when I make my final training data set, then I will actually combine or merge together unigram byte files with size of byte files to get a single feature. But for now, our three features are ready. So what are the features we got till now? We got this one just now. We already got this one, size of byte files, that also we calculated, and we also got this one. We have already calculated with the long code that will require 48 hours to run to get this feature. So three features we got out of 8, and still 5 more to go. And the next one I will probably calculate the size of ASM files. And so now I'll be calculating the file size of the ASM files. It's exactly the same process. The code is exactly the same what we applied to calculate the file size of the byte files. So initially I get the list directory of all the ASM files. Remember, we created the directory containing all the ASM files in a separate directory. So that's what now I am capturing with these files variable. And then the simple code using os.stat, I loop through all the file names in this files directory, and then append the size of the files to these variable named size bytes, and I get this size of each file with the stat info. That is, and the stat info is just obtained from os.stat, this module of Python. And then I finally create a data frame ASM size bytes, which has these extra column size for containing the size of each of the files. And this is kind of, it looks that I have the class names, the each file unique IDs, and also the size of the files in a separate column. So with that, by calculating the size of the ASM files, we are done with these many features in our planned featurization technique. So I'm done with 1, 2, 3, 4, and the next one I will calculate is this one, that bigram of byte files. Bigram of byte files. And first I will calculate the bigram of byte files, but that will give me a huge number of features or columns, but which is not necessary and not optimal, and that will really make the code non-executable because it will be so large. Because when I extract bigrams from 50 GB of byte files, it will be the number of features and the number of columns will really be tremendously large. So I will take only the top 2000 most important bigrams of byte files. So first, calculate the bigram of byte files with this function. So here is where I'm calculating this one, and I'm mainly using count vectorizer. And the most important part is this one, that count vectorizer can calculate both unigram, bigram, or trigram. So here with this parameter ngram range, I am mentioning whether it should calculate bigram, and by giving these a tuple of 2, 2, it will only calculate the bigram. So quickly check out their documentation. So this is the documentation of a count vectorizer of sklearn, and if you go to, and one of the parameter that count vectorizer takes is ngram, and if you go to the definition, So Ngram range by default takes a tuple of 1 1, which is for Unigram. So here is how to configure that the lower and the upper bound. So the tuple takes min x and max x. By default it's 1 1. So the lower and the upper, it sets the lower and the upper boundary of the range of n values for different word in grams or character in grams to be extracted. All values of n such that min x lesser equal to n and n is lesser equal to max n, obviously. For example, ngram range of 1 1 means only unigram. This is the default value of ngram. And 1 2 means unigrams and bigrams, and 2 2 means only bigrams. So this is what we are using in this code here for calculating the bigram from the byte features. And the next one we will calculate. So this is a code to calculate this bigram. Pretty simple code. It just I am taking all the files of the byte from the byte files directory, and then creating a CSV file with open root path plus featurization byte files. So I'm creating this CSV file and mode equal to W, that is write, and this is where I will be assigning these data frame, that is the data frame which includes the bigram features. And then it is just I am taking an enumeration of the file list byte files and then looping over them and applying vectorizer.transform, which will return me a sparse vector. And ultimately I am just writing a single row in this CSV file, and this single row will be repeated for each byte file. So this will be, if we have 10,868 byte files, these writing execution code will be writing that many numbers to get me the final data frame which has all the bigram of the byte files. And the next one is extracting the 2000 most important feature from byte bigrams using select k based with chi-square test. So let's do that now. So now basically before I apply the feature selection with select k based, let's quickly look at this data frame that I got after extracting the bigram from the byte files. So we have already written the full bigram into this file, byte files bigram df.csv. And now if I read that file, this is what I get. This is a kind of data frame. This is exactly the data frame that I get after getting all the feature names by using bigram. So this is my bigrams. See, it takes two sequential word or two sequential text as a feature. So 00, this is the first one, and then the next one takes this 00 and the next one, which is 01. Similarly, I get a huge number. How many I get? 66,050 columns. This is so many columns that I get. That is, there are total 66,050 bigrams in all my byte files. Now out of that, now I will extract only the top 2000 by using the select k based of sklearn. So this is the function from sklearn documentation. And feature selection is normally a technique where we choose those features in our data that contribute most to the target variable. In other words, we choose the best predictors for the target variable. And a couple of obvious benefit or obvious advantages are that it reduces overfitting, because less redundant data means less possibility of making decision based on redundant data or noise. It also improves accuracy, because less misleading data means modeling accuracy improves, and obviously reduces training time, because just look at our case. So it reduces from 66,000 plus features to 2,000 features. And select k base, this function of sklearn mainly takes the most important parameter that it takes is the score function. You can there's so many options to give the score function and basically this is a function taking two arrays x and y and returning a pair of arrays. And in our case I gave it the function of chi-square. One second. Yes, score function I give chai2, and if you look at the documentation, this is what it says, that ch2 will apply chi-squared stats of non-negative features for classification task. So this is what it will do here. Oh, 1 second. Yeah, so let's go back to our code. All right, so after applying chi-square, I create these object here, and then I applied dot fit on my x byte diagram all df, and this is the variable which contains a whole data frame. That is, after reading with pd.readcsb, this variable x byte diagram all df contains a whole bigram data frame. And on these I apply the fit function, and finally I extract the most important features. So that I get by applying this k equal to 2000, because I want the top 2000 features, and it's clearly mentioned in the document that select k best takes the k parameter, which takes an integer or an all, a string. So if you pass an integer, that will be the number of top features to select, and if you pass all, that will bypass the selection altogether. And all right, so I want 2000 features, so I pass 2000, and these whole thing is being held in this variable select k based object, and on this I have to apply the fit function. That's what I do here, fit, and supply, and just regularly to the fit function I supply the x and the y. My x is the full x of bigram df, but I'm dropping the id column here, and the class labels are the whole class labels for the byte files. And then this whole this fit function, this will give me an nd array of this form, which I am capturing with this variable. But I want to create a data frame with the actual scores, that is scores of importance for these top 2000 features. And so I do this next line, I create a data frame with pd.dataframe, and I extract only the scores from this important feature by invoking this scores, extracting the scores parameter here. So if you multiply this feature with a scores underscore, then you will get the actual scores of importance. And all right, and then in the next cell I am pretty much creating a data frame for holding my the actual scores of importance, and also the feature names. Remember, we got our final data set. The data frame that I want, that should hold both the scores and the feature names of the top 2000 features. So that's what I'm pretty much doing here. I'm first concatenating the bigram column df with the feature scores that I just created above here, and then I'm creating a data frame out of that. So and then if you just want to check the top 10 features, you can use in largest function. And here I'm just for the sake of checking or testing that it's working, that I'm applying this in largest function for the 10 largest feature names, and this is what I get if I print the head of that with 2. All right, so that was the bigram features, top 2000 bigram features on the byte files. With that, we are done with I think this one as well. So now still 3 more featurization or features to build, and that's what I will do now. All right, now that our top 2000 bigram of byte files is done, the next feature that I want to build is this one, top 500 bigram of opcodes of Asm files. So let's do that. So before we start actually hitting the opcodes of the Asm files, quickly look at the bigram function that I have written. 1 second, because I will be using this bigram function to calculate the bigram on the Asm files. Yeah, so I wrote a bigram function earlier in the file, which is the this is just going through just by the, like I discussed on the bigram, it captures each sequence of words, and in the case of bigram, it captures each couple, each pair of sequence of the words. And that's what this function is doing, that it's first I'm creating an empty string, and then I am looping through the entire argument of bigram tokens that is given as an argument to the function. And then there are two loops. One is so I have to go through each sequence of pairs, so I'm just doing I in TQDM range lane bigram tokens, and then again j in range lane bigram tokens, and then I'm just adding I and j together. So and then after adding, then I'm appending that to the to this vocabulary list for byte bigrams dot append, and just I'm appending the bigram, and the bigram, in like I said, that it's just this I and then an empty space and then the j. So and bigram token is a whole list of bigrams. Sorry for that, the noise. All right, yeah. So bigram token is just the list of it's given as an array for the whole text on which the bigram is to be calculated. Okay, now we will go back to calculating our bigram for opcodes of the Asm file. So now here first we have to understand a quick structure of the opcodes on Asm file before we apply the bigram function. So first of all, this is the opcodes list that will be supplied to the bigram function, that is calculate bigram opcode for bigram. So opcode for bigram is this list, and the way that it was derived is again by going through a research report and papers and blogs, that the most important bigrams were, sorry, the most important opcodes for Asm files were shortlisted to be these, and that's our opcode. And then we are also building a dictionary, but this is just because a little bit faster processing. So we are building a dict and then applying zip for all the files in opcodes for all the strings in opcodes for bigram. So from this list, we are creating this dictionary, and then creating a separate folder just to make the calculation clear, because there will be a lot of subdirectories that we have already created during the notebook or will create. So I'm just also creating another directory to keep some of the files separated. Now coming back to the opcode, that we already know that our opcode contains these 6 things: address, segment, sorry, our Asm files contains these 6 things: address, segments, opcodes, registers, function calls, and APIs. And calculating the opcode sequence is very important before applying the bigram, because calculating the opcode sequence for each Asm file and saving it in a form of text file is important, so that we can process the Asm file as text files, and in the text file each row corresponds to respective file. So we'll go by row to move through file by file. And I'm also noting that in Asm files, the opcodes for bigram, that is these ones, were not placed side by side. Instead, there are few words between two opcodes. That is, the opcodes occur with an interval. So during extraction of these opcodes for bigram, we need to preserve the sequence information. For example, which opcode precedes another opcode and which opcode is followed by another opcode. And based on these, a bigram data matrix of vectors is to be derived containing the bigram sequence info on each file. So first here we are creating that sequence. So pretty much we are creating a list from all the Asm files, and then reading that file with codex.open. Codex is a separate Python module which will for reading some file with and here I'm encoding with it with CP1252. You can read about it in their documentation. They have very detailed documentation here. This is a documentation for codec. Sorry. So they have given all the methods and on the encoding strings that we should use, things like that. Yeah, you can think about reading this documentation. And so we are reading those ASM files, and then with our strip and split, we are creating a line segment. It's like so our strip will just strip any empty space, and split will split it and make it into a list. And then we are creating another dictionary called sequence of words that will contain the word in the line. Uh, this is a simple code just to create a sequence, and then we are executing these function here, so that these opcode ASM files and opcode ASM bigram.txt file gets created and updated with all the necessary information, because now we are going to calculate the bigram based on that. So after that step is done, now then I'm applying this calculate bigram, the function that we discussed just now, and get a variable containing all the bigrams from opcodes for bigrams. And what is opcode for bigrams? Again, this is just this variable. And after invoking this function, after passing this list through the calculate bigram, I get opcode ASM bigram vocabulary. This is my bigram vocabulary for all opcodes from ASM files. But this is just the vocabulary of bigram. But what I need is I need a count of each bigram. That is, I have to go back to scikit-learn's count vectorizer again and get the counts of each of these bigram vocabulary. And that's what I do in the next step. In the step here under the number 45, I calculate, which is calculating opcode bigrams with above defined function and make them a feature, and then save the data matrix of feature as a CSV file. All right, so now I have got the vocabulary from the previous step, and then I'm just applying count vectorizer with tokenizer, lowercase, n-gram range 2 and 2 like I discussed, that 2 represent 2 is for representing bigram, for calculating bigram. And for the vocabulary, I pass this entire bigram vocabulary that I just calculated in the previous step. So now this will give me the vectorizer opcode, and just a regular process. I have to apply a transform on them. But before that, I do certain little operations that I'm creating a list of all the files, which is from opcode ASM files. And what is our opcode ASM files? This is this. We one second. Where is our opcode ASM files? This is such a long notebook that sometimes I'm losing track. Root path. Okay, yes. So opcode's ASM files is that the one that we already created earlier under our root project directory. So I'm just getting these. Let's quickly check the first time it was created. Yes. So here in the previous step, we created these opcode ASM files. If not os.path.isdir, then we created with mkdir. All right. So now I'm just going to create a file list from that file, and then the regular codes here, this block will pretty much, what they will do is that it will apply the transform with these vectorizer opcode, and then create ultimately it will create a data frame and create a CSV out of that. So what I do is I create an opcodes ASM bigram df.csv file with a write mode, and then I am just looping through the entire file list with an enumeration, of course, and then for each of the file I am replacing the new line with an empty string, then applying the transform method on vectorizer opcode. Vectorizer opcode we just created here, this one, and after this transform, and this transform of scipy of scikit-learn will give me a sparse metric. So I also have to convert it to a dense matrix. That's what I do here. Then update each row of the data frame with bigram counts of the respective ASM file. And count vectorizer produces sparse representation of the counts using cipers.sparse.csr matrix, and with two array I make it a dense matrix. And then ultimately I'm writing these each row I am writing this to this file opcode asm bigram df. And again, opcode asm bigram df has been defined here, that under featurization opcode asm bigram df.csv as this one. And finally I'm creating a data frame. So this looping will go through for each file of under this file list opcode, which has all the asm file and asm file opcodes. And then finally I'm creating a data frame, and if I print the data frame, this is the final thing that I want, and I get this is a bigram of the opcode files of asm files, of the opcodes of asm files. So jmp appears 0 number of times in the first file, denoted by this hash number, and it appears like 380 times for this file. So similarly I get all these column numbers and the respective count. And how many columns I have? I have 677 columns. But the next step, I'm going to extract only the top 500 from these 677 columns. And just like our previous exercise on byte files, we apply the same kind of steps. That is, we will be using select k best of scikit-learn with the score function of chi-square, and then I pass k as 500 because I want the top 500 feature, and the rest of the codes here is just the same like we used for byte files. That is, I create first I create a score list from my top feature score. And what is my top feature score is this one, that after applying the select k best, I get a list of score importance, and I can extract that with this dot score underscore method. And then I create a list, and I ultimately create a data frame for one containing the column of asm opcode bigram top feature name. So this is a feature name in the data frame, and another one will come. This is our final data frame of the top 500 bigram of opcodes of asm files after creating a data frame. And so in this cell I'm just creating converting creating a csv file from the data frame with the toCSV method. And this is what I get, that a data frame which has only 500 columns and the bigram for the entire asm file list. And so with that, I am also done with this feature, top 500 bigram opcode of ASM file. Now I will be left with only two more. So let's do the next one, which is top 800 trigram of opcodes of ASM files. So first build our trigram function, calculate trigram. It's just like the bigram, but instead of taking two pairs of words, we'll be taking three pairs of words. So this function to return all possible n into n combination of trigrams. It is just a similar kind of code that will be given a list of tokens, and then I create a string, and then I will loop through the tokens I, j, k, and then the trigram will be just token I plus an empty space plus token j plus empty space plus token k. And finally return this and trigram result. These final result will be updated or appended with this diagram, that is I calculate through the looping. So for each loop I will have one trigram, and that will be appended to this trigram result that I defined at the top, and then finally returning the trigram result. So given any list of tokens, this function will give me the trigram. And now the time to apply it on our ASM files. And the process is just the same that we applied for calculating the bigram. So we have a list of opcodes. It's a same that we used for bigram, and then we are applying these calculate trigram that I just defined above here, and passing these opcode trigrams to this function. So this will give me the vocabulary, and now I have got the vocabulary, so I need to apply count vectorizer to get the count of each one of this vocabulary, and that's what I do. Exactly the same code, only difference is that vocabulary, for the vocabulary parameter I am passing opcode trigram asm vocabulary, which is this. So otherwise the rest of the code in this cell is just the same that we applied for bigram. Only difference is that here we are calculating the trigram, so ultimately we get a trigram at the end, and we are creating a data frame from that trigram, and this is that data frame. And see the difference. Only difference is that now we have three words. For bigram we had this kind of structure, two words, because this was bigram, and now we have got the trigram and the count of that. So yeah, so you can see number of zeros are much more here, because now we are counting the frequencies that these three words together appeared in this file. So definitely conceptually you can understand, normally this should be, the number should be less, because now we are capturing, the condition is a little bit more stricter now. Instead of two words, now the condition is three words, trigram. Okay, and then top important, so this is our full data frame, but and this has 17,577 columns, because it's a combination of all the trigram, and just by the mathematical rule of combination, the number of combination of three different things taken three at a time will be more. So yeah, so but we do not want so many columns, definitely, so I'm going to do the same kind of steps here, that I want to extract only 800 features from these opcode trigrams, and again the benefits are on multiple level, that while we are extracting only the top features, we will reduce the chances of overfitting the data, we'll reduce the training time, and also our accuracy score will be better, because all the noisy kind of parameters will be filtered out. So again, this code is just the same that we applied for bigram. So here pretty much I'm applying the select k based of scikit-learn with k equal to 800, and the score function is again chi-square. From these I will get the scores, which is this method, and then I will get a list of scores. I will concat that with the actual scores and the column names, and then create a data frame out of that. And from that data frame, yeah, so that data frame, from the data frame, ultimately I will create a CSV file with a 2 CSV, and this data frame that I have printed here with the head, it is just to show the how it looks like. So here I have made use of this n largest function, which will give me the n largest 800. Yeah, so this is my final feature that will be fed into the final model. So this data frame is for the top 800 trigram on the Asm files, and you can see that column number is 800 here. Initially we got a column number of 17,500, and out of that we extracted the top 800 by important score. All right, so that completes my this feature as well, top 800 trigram files. And now I will quickly go over these last feature, but it's a very special one. You have to remember that I will create images from Asm files and take the top 800 from that. So there's a lot of concept goes here, and a lot of papers have been written here, and there has been quite a bit of discussion in the Kaggle competition as well. So I don't want to go into too much of detail on this one, because then it will become a separate video altogether. Probably I will make a separate video on these particular aspect of this competition, that how to analyze these Asm file as an image. So I will just point out some of the fundamental concept used here and how I got that 800 features, so that you can you can make sense of that. But there are a bit of details here which I will give some of the links in the description of the video, and I recommend that you may want to read through those. So this is the code for converting ASM files to images, and I plan to make a separate video on this particular specific topic itself because it needs some concepts to be properly described and explained before this code can be well understood. So for now, just know that this code converts the ASM files in the ASM directory into images, .png images, and that's the base on which this conversion is done is kind of linked to the size of the ASM files, and after doing some mathematical operations on them. So, and after we convert them to PNG, but then again the same process we have to apply. We have to get the most important pixel data from those pixelated images. So what we do is we load all the ASM images, convert it into a NumPy array, and take the first 800 pixel from each image. It's relatively straightforward approach. There are quite a bit of more in-depth approach to handling this problem, and I will refer you to some of the links, but this is the approach I took, and this code is again relatively simple, but they are connected to this code of conversion of images. So I will go into I will go in detail on a separate video on these section of the code. For now, I'm just referring you to some of the blogs that was recent. I definitely recommend that these you should watch this video as well, from this guy Jiwei Liu. It's a first place approach in Microsoft Malware Classification. So I think they own the first rank in the competition. And also in the discussion, you can also read about some of the discussion thread there. So he has also given in his notebook, he has also given the GitHub repository link, I think, and they have explained in some more details on these image conversion, on their approach, etc. So anyway, so these definitely needs a separate video altogether that I will do in a while. But for now, this is our last feature that we got, and what we got is, after we got the top 800 image, is these data frame. This one. So each file will have so many features, and of course in a corresponding number according to them. And so this is going to be fed into our final model as well as a last feature. So now we are done with this one as well. So now we are almost ready to run our final model, but before that we have to make the data frame completely finalized, merge all the individual features that we have built so far, and create a final data frame before that final data frame is fed into our XGBoost model. All right, so this is the final step of our feature engineering work that we were doing all this while. So now I have to combine and merge all these new features that I was building all this while. So I have got these 6 different features, actually 8 of them, but as we can see that the unigram of byte files plus size of byte files has been combined already, and that's one feature. And similarly, top 252 unigram of ASM files and size of ASM files also have been combined to form a single feature. So now finally we have separate 6 features. So 1, 2, 3, 4, 5, 6. And also you will remember that as and when I was building features, I was creating a data frame from that feature and saving that data frame as a CSV file. So now the first step is that all we have to do, we have to read those CSV file and get them in a variable. So 6 separate variables after reading 6 CSV files for all these 6 features. And in this cell, that's what I'm doing. That the first one is unigram byte features with size, and for that I'm just reading these featurization, Unigram byte feature with CSV file. And remember, we have already, just to repeat again, that these file is what I have created during the feature engineering work. So when I created these byte feature and the size of byte files, I combined them to form a data frame and then exported them as a CSV file and saved it in the featurization folder under the root folder of the project. And now I'm just reading them. Similarly, I'm reading the CSV file for the ASM files. So in this next line, exactly that's what I'm doing. That during the featurization or feature engineering steps, we earlier, when I calculated the Unigram ASM feature on the ASM files and the size of the ASM files, combined them and exported them as a CSV file. So now I'm just reading them. But here there's a little code here for dropping few of the classes. So I'm dropping class RTN, dropping few of the features. So the features I'm dropping is class rtn.bss.code. And why? Because during the EDA, I found out that these features were not contributing to the classification as much. So you will see that probably I have not discussed particularly on this part that how I found out that they are not contributing enough, but I am definitely included that in the notebook. So you will get that when you get to see the notebook. So yeah, so I'm just doing the same thing and dropping these features and getting these variable containing the features for ASM file Unigram and ASM file size in a single variable. And so the similar thing I'm doing for top 2000 important byte diagram DF by reading the same CSV file that I saved during the feature engineering work. Same for this one, and this one. So now I have got 6 variable by reading 6 CSV file with pd.read_csv, and they are my final features. So they are the final data frame that is going to be fed in the final model XGBoost. But before feeding them, I have to combine, or I have to merge these variables in a single data frame, because right now they are 6 different data frame. So that's what I'm doing in this next cell here. So initialize a data frame for representing the combined features and set it equal to the Unigram byte feature with size. So I'm just initializing these final combined feature final. This is extremely important. This is what is going to be fed to our model. So I'm initializing it to be this variable Unigram byte features with size, and that just has been defined here when we did the pd.read_csv, this one. So it is just, I'm just initializing this data frame to be equal to this, and then now I have to merge the rest 5 to this data frame, and that I'm doing with a little bit of code. I'm just declaring a list containing the other 5 that I just defined here, and then I'm combining them with this little code of pd.merge and looping through each of the elements of this list, and then I'm doing pd.merge with the first initialized combined feature final df. So after this line of code, I will have the combined final df, which has all 6 data frame of features inside it. And now again, I'm doing a 2CSV to save it as a CSV file. It's just a good practice too, because now I'm dealing with such a huge data. At no point of time I want to lose, for some reason, my computer suddenly malfunctioning or Jupyter Notebook suddenly crashing. I don't want to lose any data point at any point. So at each step here, because this is the final step, I want to save it as CSV file. So if something happens, I can quickly just start from here by reading this CSV. Because remember, some of these codes from here in this notebook took almost 2 days to run. So you have to be extremely careful with this notebook if you plan to run it ever in your local computer or in your cloud machine. All right, so now this is our final combined feature, the combined feature final df.head, and this is this. We have total 1628 columns. Remember, initially we had a lot of columns. We had more than probably 70,000-80,000 column, but after we did all the feature extraction with the most important feature using sklearn select k best, Now we are left with 1628 columns only. And now the final step of the regular step of a train, test, and cross validation split. So I'm going for a 64% train, 16% cross validation, and 20% test. And so it's just normal code here. I'm just reading this final combined CSV, and then I am doing a fill NA of the fill NA 0 on the X values. And yeah, so, and the Y value also, I'm just taking the class from the final merge data frame. I'm only taking the class, and the for the X values I'm dropping ID and fill NA with 0. Okay, and now this so this becomes my X and this become my Y, the actual ones. So now so on these I will be splitting them. So now this is the final, the famous train test split function on this dataset, and I'm getting a train dataset, test dataset, and cross validation dataset, and I'm printing the shape of them as well. So my X train is 6955 by 1627. The number of columns definitely would be same for each of them, but number of rows in my train is 6955, in my test is 2174, and cross validation is 1739. Okay, so now everything is ready for our final XGBoost model to be trained, and that's what I'm doing here. First, I'll be using randomized search CV to get the best params. So I'm just declaring a classifier with Xgb Classifier, and then setting all the params. So learning rate, I have given quite a bit of reasonable range here, starting from 0.01 all the way up to 0.2. Number of estimators also 100, 200, 500, 1000, 2000. Max depth 3, 5, 10. Call samples byte tree is 0.1, 0.3, 0.5, and 1 subsample. And tree method, this is important. I will be running this both in my local machine and also in Google Colab with the GPU. So you have to specify these to take to use the GPU, the tree method, GPU hist. And then I'm creating this random classifier with randomized search CV, and when the fit function is applied on this random classifier, it will give me the best params, the most important things before I run my XGBoost. So I get the best params to be these values. So this is the best params that I have, and I will be using exactly these parameters in my final XGBoost. So this is the final running of XGBoost with best hyperparameters that we got from above randomized search CV. So here number of estimator is I'm taking it from the from these best params. So I'm just using this notation here, random classifier dot best params underscore, and then you can pass the exact string for the number of estimator, which is n estimators, and it will give you whatever was n estimators, that is 1000. And similarly I do for subsample, max depth, learning rate, call sample, byte tree, and tree method is definitely we have to use the GPU, so the GPU hist. And then the next code is just a regular boilerplate code of Xgb Classifier. So I am getting Xgb Classifier with best hyperparams and passing the full parameters. Number of threads I'm specifying to be -1, so that it will take whatever number of cores or threads are available in my machine. So for that time, if you're running it in the local machine, it will almost become unusable for any other job, because this Xgb Classifier will take up all of your CPU cores, because I have specified -1. So you can of course experiment here. You can specify 2, 3, or whatever you are comfortable with. And yeah, so finally I get the calibrated classifier CV by using this function, and then finally I apply the fit function on my X train final merged and Y train final merged. By the way, just forgot about a quick point, and that's kind of very important. So I'm just going back a couple of steps here. So before my final train test split, when I got the combined feature final df, we have to normalize it. And this step, it was mentioned in the, it is definitely mentioned in the notebook, but I forgot to mention it separately. But this is very important step, that we have to normalize this combined final data frame. And I created a custom normal. It is not really custom normalize. I could have used some of the ready-made normalize function available in scikit-learn or some other packages, but I anyway created my own normalize function here in the notebook. This is that function. It's just regular min max normalization, but anyway, I have referred to this Stack Overflow post here, so you can check that out. It is just taking the feature name, each feature name minus the mean value divided by max value minus mean value for each of the feature values, and then it will give me the result after normalizing it. So that's we have to apply after getting the combined final data frame, because otherwise the data here hugely varies. There is absolutely huge variation in the data. Somewhere it is more than 90,000, and many places it is just 0 or 0 point something. So you definitely have to normalize it. Okay, now coming back to where we were, that is yeah, we have already we have already run the XGBoost, and we have calibrated, we have also applied calibrated classifier CV, and we got this SIG classifier, and on this I apply the fit function with the actual, that is a ground truth X train and ground truth Y train data, and that will give me all the base to get my predicted value of Y's. So this is what I'm doing in the next cell. That is, I'm again taking the n estimators to be the same as from the randomized search CV, whatever we got from its best params. And this is the important part, that before, remember the evaluation of these competition was multi-class log loss, and so for that first we have to calculate the predicted Y train, so predicted value of the Y's. So that's what I'm doing in this simple single line of code. It's super simple. I just apply predict proba, because this will give me the probability estimates on SIG classifier, and SIG classifier is what I got after using after applying calibrated classifier CV, and then on SIG classifier I already have applied the fit method. So now I got the predict Y train by using this method predict proba, and as an input to this function I just applied the X train final merge. This is the completely trained value of X, and with that I can apply the log loss, which is a ready-made function here that we have already imported. So this is what I'm printing with best number of estimators of n estimators. N estimator is just this number. I got a log loss of this. So for the log loss function, you have to supply the actual ground truth Y values and the predicted Y values. And I got a log loss of 0.007, which is, you can say, it's pretty good. It's not within the top leaderboard, definitely, because in the to be on one of the top in leaderboard in this competition with such a huge data set of half a terabyte, you really need access to superbly powerful computer, like having 48 GB plus of VRAM, similarly powerful GPU, or even TPU. Many people have actually have access to multiple TPU, tensor processing unit, to handle this competition. And I don't have access to these powerful GPU just at this moment. So yeah, so with these our reasonable resources, I could achieve 0.007. But remember, my whole training was done only, my whole training and the whole notebook was done only by dividing the trained data that was given in the original competition itself. So I splitted the trained data, that is 200 GB, into 64% train, 20% test, and 16% I think cross validation. With this itself I got the this log loss. But if I train on the entire train dataset, that is if I train on the entire 200 GB of train dataset, probably I would have got a little bit of improved log loss. But anyway, this 200 GB itself was such a huge fight for me to run. This was hell of a notebook for me to run. I probably spent completely 6-7 days to handle this notebook from beginning to end. So yeah, with these LogLoss, it's kind of okay and kind of good, I would say. And but there's a huge possibility of further analysis and further further feature engineering technique to be applied for this competition. This is such a beautiful explanation example of the finest feature engineering technique that you can apply, because you are given just a huge set of files and your job is to derive so many innovative features out of those files only. So here I have mentioned a few of them by reading some of the discussion and some of the research papers on this, that how people who have achieved really good score and one of the top 10 in the leaderboard, they have used many more features indeed to get their scores, like names of the imported function, because some of these malware, most of the malware files indeed will have imported functions in them. So the names of those functions could be an important feature, and analysis could be done on them. Then the libraries that those files used, the number of procedures used, computing the constitutionality of the executable, the number of LOC references in the .asm file. Then further, according to some papers, the malware content is often encrypted inside the binary, so we could introduce some encryption related features, computing entropy over a sliding window of half byte sequences. These are definitely some more sophisticated and complex features that we could have built, but it will take similarly that much time to process and compute and analyze. Then further extracting some statistics of its distribution, 20 quantiles, 20 percentile, mean, median, STD, etc. Statistics of first order difference distribution and parts of the entropy sequence, computing compression ratios as an approximation of Kolmogorov complexity. I don't really know what this is, so I have to read up. So yeah, these are some of the more important, some of the more ways of innovation you could bring to this competition. And definitely in those cases you will build a more powerful model and you will get your log loss even much more improved. I definitely suggest you read about their discussion forum in the competition. So this is my notebook in the Kaggle competition. So if you go to the competition, sorry, where is the competition? Yeah, so this is the competition page, the overview page, and I definitely suggest you check out the discussion forum. So I'm just will refer you to another beautiful discussion. He's a grandmaster in Kaggle, and he has described the 7th place solution here. And just by reading, you will get so many ideas how the modeling and analysis and feature engineering can be improved for this competition. Like they have used counts of various objects such as hex codes, hex 2grams, assembly language commands, then hashes of specific parts of the ASM file, such as each of the first 50 lines and specific properties of the ASM files, for example, segment type, segment permission, etc. I have also partially introduced some of the segment type feature engineering during our analysis of ASM files, but these that he has mentioned here is definitely more advanced. And yeah, so with these they have achieved private LB, they have achieved a score of 0.006, which is definitely much better. The final CV and NV log losses were for them is 0.005 and 0.004. Yeah, so to get this kind of log loss, you really have to implement even more feature engineering and more advanced computation here. So yeah, so look at them. These are really some of the great feature engineering for length of the IDAT section, length of the .data section, length of data section. Yeah, these are just beautiful example of feature engineering. All right, so with that, this long video comes to an end. There's definitely more work, scope of much more work to be done on this competition if you are interested. And thank you very much for watching. And if you like the video, please hit the like button. And if you have not subscribed yet, like I said at the beginning, I plan to upload videos quite frequently, averagely 2 times to 3 times per week. So please consider subscribing to my channel. Thank you very much.